Hello guys, we're from Group 1 Calculus class, and today in this video we're going to explain about Chapter 1, and that is about limits. And we're going to introduce ourselves. My name is Faiz Rafi Darmanto.
My name is Romulo Schiffler.
My name is Farah Fadila.
My name is Areta Nivita.
My name is Azahra Prashanti.
Please enjoy the video.
Sure.
So explain a little bit about what is limit and why we use it. So basically limit is a mathematical way to explain how a function will behave if they approach certain rules, certain values, and theorems of limit. First, we're going to start with contents rule for a limit. If a and b are constant, and we have a function represented by a limit of x approaching a of b, then the value would be b. Now we're going to go to the identity rule for limit. So if a is a constant and limit of x when x approaches a equals to a. Scalar product rule for limit. So in this case, c is a constant, and there is this limit of function and point a. When we have a function like limit of c plus fx of when x approaches a, we can write it as c plus limit of fx when x approaches a equals to c times L, because L is limit of fx when x approaches a. Okay, so for the sum rule for a limit, we have two or more limits of a function in the same point. So in this case, it's limit of fx when x approaches a equals to L, and limit of gx equals to m when x approaches a. So if you make the sum of these two functions when x approaches a, it's going to be represented like this. However, you can rewrite it and be like limit of fx plus limit of gx when x approaches a. And now you can substitute the value of fx, limit of fx equals to L, and the limit of gx equals to m. So it would be m plus m. The difference rule for a limit. So basically we are gonna repeat the same thing for the sum rule, but with the minus. So when x approaches to a, we can rewrite it for limit of fx minus limit of gx when x approaches to a. And now we can substitute the values of the limit of fx and gx to be L minus m. Now we are going to the product rule for limit. So we have limit of fx and limit of gx when x approaches to a. The fx would be L and the gx would be m. And when we make the multiplication between these two functions, it will be limit of fx times gx when x approaches to a. And we can rewrite it like limit of fx times limit of gx when x approaches to a equals to L and m, which are the values of fx and gx respectively.
Okay, now I'm gonna explain about limits of trigonometric limits for this. There's three actually. For the limits t approaches to 0 is only for 0 of sine t over t is always gonna equal to 1. And then the second special is limit of t approaches to 0 of 1 minus cosine t over t is always gonna result into 0. And then for the last one, limit t approaches to infinity of sine t over t is always gonna result as 0. Limit of x approaches to 0 of 2 sine squared 2x over x squared. So here we move the 2 away from the limit, right? We do like this. And then we work on from this both of sine squared 2x and x squared. So we write it like this: sine 2x and sine 2x and x. We write it like this so we can divide it into here, so it's easier to see. here again, we have to put it like, so there's this special trigonometric limit, right? So you have to write 2 over 2, like in the first example, for this one and this one. From there, we're gonna get this limit x approaches 0 sine 2x over 2x. And same applies to this one. Sorry, limit x approaches to 0 for this one. This one is gonna fulfill the special trigonometric limits of the first one is gonna equal to 1, and this one also is gonna equal to 1. The 2 from above here, the 2 from here is from the first question. We put it outside, so it is easier for us to work with the trigonometric limits. And then here you get these two from 2 over 2 and 2 over 2. So we can put the 2 under and pair it with the x under, right? So it's going to 2 times 2 from here, 2 from here, 2 from here, and it's times 1. This is the special limit function, and it's also going to equal to 1, the special limit function. So it's 2 times 2 times 2 is going to equal to 8.
Limit at infinity are used to describe behavior of a function as the independent variable increase or decrease without 1. And we write like this: limit x approaches to infinity or limit x approaches to negative infinity. The example of limit at infinity. When we're going to solve about this problem, we need to know what is the highest degree of this function. The highest degree of this function is x squared. So we are going to divide all of the numbers here with x squared, like this. But if you can see, if this is 0, and also for this one and this one, the value that we got here is only 2 divided by this 1. So the answer is 2.
Infinite limit. Infinite limit is limit that have a value of plus or minus infinity, where the function grows without bound as it approaches some value of a. For f of x, as x approaches a, the infinite limit is shown as limit x approaches a plus infinity, or limit f of x approaches a equals minus infinity. So here are some facts about infinite limit. If a limit x approaches c, f of x equals to infinity, and limit x approaches c, g of x equals to L, c and L are real numbers. First, limit f of x plus or minus g of x equals to always equals to infinity. The second one is if L are greater than 0, then limit x approaches c, f of x times g of x always equals to infinity. The third one, L less than 0, limit x approaches c, f of x times g of x equals to minus infinity. The fourth one, limit x approaches c, g of x over f of x equals to 0. So here we have a form of limit at infinity. Limit x approaches to infinity, square root of ax squared plus bx plus c minus square root of px squared plus qx plus r equals to L. So if we have this form, we can use the fast way of doing it. So the result of L equals to infinity applies if a is greater than p, and L equals to minus infinity, it applies if a is lesser than p. L equal to b minus q per over 2 square root of a. It applies if a equals to.
A function f is said to be continuous at x equals to c if first, f of c is defined. Second, limit f of x as x approaches to c exists. And third, limit f of x as x approaches to c equals to f of c. Other than that, we can say the graph of a function can be described as a continuous curve if it has no breaks or holes. And if one or more of the condition of this definition fails to hold, then we will say that f has a discontinuity at x.
So
equals
for
to
the
c.
example, we have f of x equals to x squared minus 3 when x is less than 2. Then we have 2x minus 3 when x is greater than or equals to 2. To check for continuity, we need the limit f of x as x approaches to 2 equals to f of 2. And for note, the limit only exists when the left-hand limit is equals to the right-hand
So
limit.
let's check our left-hand limit. Limit as x approaches to 2 from the left-hand side means we want x less than 2. So we're using x squared minus 3. Then we put 2 squared minus 3 is equals to 1. So for the right side, we need x greater than or equals to 2. So we're using this 2x minus 3. Then we put 2 means 2 times by 2 minus 3 is equals to 1. So as we can see here, the left hand side limit is equals to the right hand side limit. It means that this function is continuous everywhere.